Welcome to the channel. Matt Makens here. What are we chatting about today? Why in the heck do we care about El Nino or La Nina? I visit with clients all the time. Whether presentations, written monthly reports, they can be in Australia, Canada, Mexico, the US. Everybody is reliant upon this thing, El Nino or La Nina. You don't believe me? Here's a visual. Look, these are El Nino years, winters since 1950. Warm to the north, cold to the south, wet to the south, dry to the north. Compare that to La Nina, and there's a major difference. Look at the flip. You basically have flipped that pattern by going from this El Nino thing to this La Nina thing. And it gets even more nuanced than this. Across Canada, there are similar impacts. El Nino years, La Nina years. You increase or decrease those colder winters, you increase or decrease the snow, and you can increase or decrease drought. All because of this silly thing called El Nino or La Nina. But is it truly silly? Let's break this down. What is this phenomenon? And I should point out here that today we're just chatting about the El Nino or La Nina of the Pacific Ocean. You may hear similar terms used in the Atlantic, but today let's just focus on the Pacific. Imagine the Pacific Ocean, just a giant bathtub, okay? Just put that in your memory. Normally, the water kind of just sloshes back and forth, and it's relatively predictable. I mean, we have a good understanding of ocean currents and how things have moved around historically, but sometimes the rhythm kind of gets disrupted. But El Nino occurs when the water in the eastern Pacific Ocean becomes unusually warm. The warmth can trigger changes in the atmospheric pressure up above, patterns of thunderstorms, wind flow. All of these things get impacted by just warming up the bathtub right in this area. On the other hand, La Nina, that's when we are unusually colder in these equatorial Pacific waters, and this cooling also has an impact on the weather patterns, changes pressure patterns, changes wind. All of these things alter the weather pattern globally. So let's visualize this for a minute, okay? If this is our big bathtub right in here, equatorial Pacific, this is the 1983 El Nino event. The Pacific here, much warmer than average, that's why I colored it in red. And then here is our most recent La Nina, the 2021 version, and it's much colder in the same giant bathtub, if you will. So blue for colder than average. It's not that big of a difference, okay? Yeah, the ocean is massive, and the heat content of the ocean is enormous, right? But we're just changing this area of ocean from about 2 degrees Celsius colder than average to 2 degrees Celsius warmer than average. And really the technical definition of El Nino or La Nina is just being at a half a degree Celsius above or below average. That's for the US standards. A lot of global standards too. If you're following along like the Bureau of Meteorology out of Australia, they use 0.8 degrees Celsius as a threshold for El Nino or La Nina. But in the end, what separates one from the other is just 1 single degree Celsius in that ocean condition. Here's a different way of looking at it. Flattened out the map. This is a satellite projection of sea surface temperatures. And again, just looking at the surface of the ocean and reading that temperature and saying whether or not that's colder or warmer than a 30-year average. I've highlighted some black boxes on here as well. Each represents a different kind of ENSO region. ENSO is El Niño-Southern Oscillation, and that's where we look for El Nino and La Ninas. But anyway, each of these boxes correlate to different global weather pattern phenomenon. So like the smallest box there near South America, that's the 1.2 region, it can correlate to different seasonality changes for the US, or maybe has a bigger impact on South America versus Australia. So these boxes are used in different ways to tell us different patterns on more regional scales rather than global. The main region is this one. I've highlighted it here. It's 3.4. That's basically what it's called, but that's the main region where we're looking at ocean conditions. And within that region, we just track the temperatures over time. What's the average sea surface temperature of that box? And here is an example of 2024. We had an El Nino early in the year. January's on the far left. We were just shy of 2 degrees warmer than average. By May, we were in neutral territory, meaning we were between that half a degree plus or minus area, and we've been remaining there. To get to La Nina, we got to get down to half a degree below average for about 3 months or so. Or in Australia, you got to get down to 0.8 below average. But why on earth do we care about a fraction of a degree Celsius? It matters. This is where I meet with a lot of clients on understanding the difference in El Nino and La Nina for one, but the strength of those events is wildly different. Here's the visual I use. Strong El Nino events, very warm to the north, cold to the south, very wet to the south. you weaken El Nino. You hit a neutral phase. And again, we're talking about fractions of a degree Celsius difference in those ocean conditions. Then you get weak La Ninas and strong La Ninas. And you can see the nuances here, the changes, the variability from one phenomenon to the next. And even sitting in neutral territory, that can behave much more like a La Nina than anything else. And how is this done? Well, by warming that area of ocean up or cooling it down, you change where the jet stream is. Perhaps you've seen these images out there before. NOAAclimate.gov. Great visual, so I'll use them. In El Nino patterns, we have warmth from Alaska down through much of Canada into the northern U.S. It's wetter and colder down across the southern U.S. and parts of Mexico. That's because we've kind of added an enhanced jet stream, if you will. Comes from ballpark near Hawaii. Very humid tropical flow of air hits the southern U.S., and that makes sense why it's wetter there. It also makes sense why it's warmer to the north, because we're not tapping into cold. We're not having a strong northern jet stream that grabs cold air from Siberia or the poles and pulls it in. That's with El Ninos in the winter. What about La Ninas? That's when we get the stronger jet howling in over Russia, grabs cold air there in Siberia, shoves it toward Alaska, pulls that colder air down across much of Canada into the northern U.S. The result is we can be wetter than average across the Northwest and parts of the plains and parts of the Great Lakes into Ohio and Tennessee valleys. Now, you got to flip the coin, though. Weather is a balance, after all. That means drier and warmer across the southern states. And just changing that ocean condition changes, on average, where the jet stream flow is. That's what brings about all of these changes weather-wise. But this isn't to say that the jet stream has to be in this position. It's highly variable, especially based on the strength of El Nino or La Nina. And it goes beyond this winter phenomena. I showed you the cold seasons because that's when El Nino and La Nina have the biggest impact on the states, but there's also an impact tropical-wise. Changes to the frequency of hurricane events across the Pacific or the Atlantic change based on these patterns. Okay, let's take a break for a minute. I gave you the data showing you how different these things are and generally speaking why they're different, but how do these things occur? What's driving this force? Well, the key to understanding this just lies in how the ocean and the atmosphere work together. We call that coupling. Normally, trade winds, which is just the surface, near surface wind flow, basically they're usually from the east to the west across the Pacific, okay? And that pushes warmer water toward the west. Now, this creates a difference in sea surface temperatures just by blowing and pushing, driving that ocean water, if you will, from the east to the west. And during El Nino, these trade winds weaken. Not very strong, so they're not pushing that warm water or trapping it west. They're allowing that warm water to kind of slosh back, in our bathtub analogy, back toward the east. And that disrupts the normal atmospheric flow up above, just as we chatted about. In La Nina, the trade winds are stronger here. Usually you have a high pressure area down over, say, the Easter Islands, and that strengthens, and as a result you get stronger winds from the east pushing that water to the west, and we're starting to get upwelling, which is colder water down below the surface of the ocean, comes up around South America and arrives in this El Nino, La Nina region and cools that area off. That leads to different weather patterns. But by changing the ocean and the atmosphere, when they work together, again we call that coupling, we can measure El Nino in the surface conditions and El Nino or La Nina in the atmospheric conditions. Perhaps you've heard of the SOI or MEI. Those kind of things drive how the atmosphere is behaving in response to the ocean, that coupling. Is it a strong coupling or are they not very strong at the moment? And all of that ties into our local weather across North America, across Australia, across South America, leading to big time changes based on the strength of all of this flow working together, like gears in an engine. It's probably worth noting where in the world did just the name come from? Well, the term El Nino comes from Spanish and means the little boy or Christ child. It was originally given to the warm ocean water that would appear near the coast of Peru and Ecuador. And that was around Christmas time. That's why it makes sense that it was called the Christ child by those people at that time. And there were changes to fishing habits and fishing patterns for that area. So they were very observant, knowing the ocean changes, temperature changes, and and food source changes. Now, over time, the term has evolved to refer to kind of the broader climate pattern, not just that localized fishing pattern there across the coast. And if we look at El Nino's impact globally, it's a precipitation driver as well as a temperature change. But I just want to quickly illustrate the differences in El Nino, shown here, and wetter or drier areas. Notice the drier pattern from southern Mexico into much of Brazil. Drier pattern from Australia into Southeast and Central Asia. Even India's monsoonal flow can be disrupted during El Nino years. Let's compare that to La Nina. You almost flip the book on everything, right? You get moisture into southern Mexico, parts of South America, mostly the northern side. But drought sets in for the southern U.S., drought sets in from southern Brazil into Argentina. Things that we are seeing over the last several decades with La Ninas. And for Australia, much of Southeast Asia, into parts of India, we enhance the moisture flow. It's all about Mother Nature's balance, the gives and takes. Now, when it comes to my clients, okay, we're talking mostly ag, beef industry, there's some energy folks, there's some public works, there's some water resources, there's ski areas, all these kind of things. How do you talk to them about these changes? Well, history is one. History is a great guide. What has history done with these El Nino, La Nina events, and what's been the result? We also can break down computer modeling, and perhaps you've seen this stuff. And when you hear about computer modeling, when it deals with El Nino or La Nina, we're talking about the sea surface temperatures in that box, the 3.4 region I showed you a moment ago. So we're not really talking about the atmosphere at all. When you hear forecasts for El Nino or La Nina, it's a sea surface temperature forecast that you're given. You may see lines like this, kind of a spaghetti plot, if you will, kind of like this. Talks about the strength of the event, which we've already talked about today and how nuanced that can be. But it also talks about how the life cycle of these events goes on. And perhaps you're more familiar with this one. This is a graphic that comes out of NOAA. Climate Prediction Center puts these out. The probability of being in La Nina versus being in neutral years versus the development of El Nino based in a probabilistic sense. And that, again, is just that ocean area. But when you talk to clients, talk to you folks with these snowfall outlooks, those kind of things, it's so much more than the ocean. Again, going back to that term coupling, the ocean and the atmosphere work together in different ways with every single event that comes down the line. So knowing the strength of the atmospheric pattern, the strength of the ocean pattern, you develop these longer range forecasts that can go out months and months and months in the future and have better risk management protections for folks knowing these basics. I want to leave you with a final thought here, all right? These El Nino, La Nina things, they last on average about a year, year and a half. The last La Nina we had was 3 years. It was historically long. What's driving this? It feels like we've been in more La Ninas than El Ninos, right? It feels like when I was growing up in the early 80s, man, the snow would be epic where I lived. Result of El Ninos for my area. But things have changed. You've all said the same thing. When I was young, weather did this. Now it feels totally different. Well, something happened in the late 1990s, subject of a future video. But prior to 1998, we were more frequently in El Nino events. Since 98, we're more frequently in La Ninas. You don't believe me? Here's a year breakdown for you, okay? 20 La Nina events since 1921. So 33 years worth of La Ninas, at least when this video was recorded. 10 were single year events, 10 were multi-year, being 2 to 3 year long. 5 of 6 multi-year events have occurred since 1998. So we're in a pattern globally that favors La Nina versus El Ninos. And what is that driving force? Well, something again for a future video, but things called the PDO, AMO, which are very slow to change, but they drive these multi-decadal patterns of drought and surplus areas. But again, we'll chat on that in a future video. So today, our giant bathtub analogy of that equatorial Pacific. If that bathtub is warmer than average, a lot of energy there. If it's colder than average, less energy, but they change the global patterns. And I showed you today the difference in El Ninos, precip and temperature orientations, versus La Nina years. Huge difference. And then it gets even more minuscule than that when you break down strong, weak to neutral events. They're all wildly different, but they fit consistent patterns based on the ocean and the atmosphere working together, not just across the states. It's across North America. Canada has these impacts too. That's why when I visit with clients, this is the subject. This is what we start with. El Nino, La Nina, the strength of the event, the projected strength, and how we've been impacted by these events in the past.